Hello, everyone. I'm Paul, as most of you know, and I'm a senior software engineer here at Not the High Street. So today, I want to talk about load testing, but before we do that, I want to kind of give it some context as to why you should care about this stuff. So I'm going to ask a philosophical question. What's the purpose of the software that we write? Any suggestions?
Make money.
Make money? Yes, that's a good one. Yes.
Make the world a better place.
Make the world a better place. Yes. Solving problems. Yes, that's all a viable reason as to why we write software. So generally, I like to think of software as having utility in the economic sense, not in the technical sense. So there's several reasons why I write it. So obviously, there's end users and customers, the people who we're building this software to use, and we're probably building it for them, maybe. But we might not. We might just be building it for our employer because they told us to. And ideally, we're trying to write software that helps them achieve their goal. And the business owners, the people who are paying for this to be built, they talk about monetizing value, right? So they're saying, well, if we build these things, then we get money in return for whatever the software does. So we spend a huge amount of time thinking about those things. Like I'd say 97% of conversations about how we build software and why we build software is focused on these things, right? So end user goals and is it making as much money as it possibly can do and so on. And we care about ease of use and we care about features. And some of us care about code quality and lack of bugs. Some of us less so. I mean, I don't always test my code, but when I do it in production because I'm very big and very clever. So we think in those terms. And quite often we don't spend enough time talking about performance. And I think performance is a really important part of that utility thing. So performance, responsiveness and speed of execution, I think it matters to customers. And we can prove it matters to customers because whenever any e-commerce platform, any web application in the world improves their performance, and different companies have different experiences. But they talk about, well, we got higher conversion rates and we get higher return rates. People come back more often. And it's valued more than slower competitors. The often cited figure for Amazon is that for every 10 milliseconds they save on a page render, conversion goes up by 1%. So that's quite sizable, right? That's their rough metric. And they've actually A/B tested. They've actually deliberately slowed pages down to see if it still holds. And that might not be the case in every web application, but it's certainly very important. And a company such as our employer, Not on the High Street, clearly conversion rate's very important. It also matters to business owners, teams that run this stuff. Firstly, because of all that customer value, right? So we want our customers to be happy. But there's also a critical aspect that all this code isn't running on the customer's hardware, it's running on ours. We pay for it. So if it's slow and we need lots more servers to be able to deliver the same thing, we have to pay more money. And so therefore it matters to a developer because otherwise we're making the product less valuable. It's less profitable, right? If I'm having to spend more money to run this thing, then there's less money to go around for other things like salaries. So you could argue that everyone wins, right? The customer wins because they get a better experience. The business wins because they get more revenue and they get more profit. And we win because we get to keep our jobs, right? So I think performance is fundamentally critical and it should be at the forefront of every single story, every single feature that we build. However, this is a good line. Premature optimization is the root of all evil. This is often cited. I first learnt this when I was young. Let's just say young. However, I like to ask, who knows who said this originally?
I can't remember the name, but I do know that it's often taken out of context because it's missing the remainder of the statement.
Well, it's funny you should mention that, Nick. Because we're going to look at the context of this. So often it's used as a kind of thing like, well, I'm not going to look at performance optimization because it's the root of all evil, blah, blah. It was originally written by Donald Knuth in a paper called Structured Programming with Go-To Statements. This paper actually, as an aside, is quite fascinating. Who's heard of the phrase, go-to is considered harmful? The go-to statement is considered harmful. Anyone heard that? Yeah? Do you know who wrote that? That's Dijkstra, another computer scientist. In 1974, Donald Knuth wrote this paper saying, actually, go-to is pretty awesome. if you use it right. And he uses an example in this. He's going through a very trivial example, really. It's searching through an array, and it's trying to find the index of this value. I want to know the first incident value 7 in this array. So it's a search algorithm across an array. And as a follow-on to this, he writes this. He says, programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their programs. And these attempts at efficiency actually have a strong negative impact when debugging and maintenance are considered. We should forget about small efficiencies, say about 97% of the time. Premature optimization is the root of all evil, yet we should not pass up our opportunities in that critical 3%. It's this bit at the end that everyone keeps on forgetting. And he's actually saying you should really care about performance in these particular parts. The bit about saying impact when debugging and maintenance, his argument is at the time, bear in mind this is written in 1974, a point I'll come back to, is that if you start refactoring code to make it super efficient, it then becomes less maintainable. And that's his kind of argument, is you're optimizing, you're making it harder on yourself in the long run. But why 3%? Why is it he's saying, don't care about it 97% of the time, care about it 3% of the time? Well, that number actually comes from the fact that the example he's citing, that little array search, it's about 3 lines of code. And the original program is about 100 lines of code. So he basically says, but this 3 lines is the job of the program. The rest of it is about setup and configuration and loading up the array and getting everything working, and then we do the work. So he's basically saying you could optimize all of that as much as you want, but if you make the gain in that 3 lines of code, let's suppose you get 50% better performance, you will make the overall program 50% faster. So in actual fact, what he's saying is optimize things that are like in small loops that are really critical. Going on in the next paragraph after that bit, he talks about how a good programmer should not be lulled into complacency. Obviously this is 1974, so all programmers were men with beards. Thankfully we live in a different world. He'll be wise to look at the critical code, but only after that code has been identified. It's often a mistake to make a priori judgment about what parts of a program are really critical. Since the universal experience of programmers who've been using measurement tools has been that their intuitive guesses fail. I write this piece of software and I go, that bit's going to be slow. I'm probably going to be wrong. He's saying, no, what you need to do is write your software, measure it, and then make the assessment as to what's going to be slow. What's kind of interesting for me in this is that in a loop, that 97% of the runtime is from 3% of the code. This was written in 74. The internet didn't exist. Well, it did. It was ARPANET. The web certainly didn't exist. No one was building web applications. Very few people were building client-server applications at the time. It was mostly mainframes. And he was mostly working on things that are effectively batch processing jobs. The web's quite different to that. So in actual fact, he talks about that we should be caring about this specifically in the context of you're probably not non-IO bound applications. The web is by definition IO bound, right? It's input-output. You're taking some input and you're going to, as quickly as you mechanically can, produce an output and get it back to the user. So in actual fact, it falls outside of this premature optimization, root of all evil context. And in essence, that request response cycle that is the web, right? Get a request, do stuff, throw it back. That is the inner loop. Like 97% of our performance is that loop. So when you're writing web applications in particular, you really should care about optimization. It's really important. Every request response cycle has the potential to completely destroy you. Now, obviously, not applications have things in them, some of which are only called some of the time, and some things are called all of the time. And obviously, it makes sense to take a holistic approach. But I would argue that this whole thing about premature optimization, don't do it, I actually think that you should be taking it quite seriously. And I think the trick to that is being able to identify when you should really, really care about it. And we don't really do that very well as an industry. So that in a loop within the web, you can imagine request response cycle. Request starts, I'm going to pass and validate some user input. That includes, the URL. I'm going to do some lookups perhaps in data stores. I'm going to pass the output of those lookups. I might do some cache management and validation. There might be some business logic going on, rendering a result into JSON or HTML. Now, all of that could be considered. The whole thing needs to be optimized. It could be just one of those things is particularly slow, so slow SQL queries. If you're rendering a result into JSON, or particularly in Rails, if you're doing this rendering into JSON, God help you if you're using Rabble, you'll be waiting all day. It's particularly slow. So you then have to start being able to break down these chunks. Classically, people talk about application performance management in these kind of terms. So there's the end user experience monitoring, which is kind of, how long is it taking for a page to render, the full DOM paint time, etc. There's application runtime architecture, less interesting, perhaps. User-defined transaction profile or business transaction management. So this kind of how long does it take for them to actually complete this particular transaction? There's application component monitoring, which is probably where we spend most of our time as developers when we start looking at performance. And then there's actually data analytics around the reporting and actually understanding what the application is doing. That's all kind of well and good, but most people look at that and go, well, I don't really know where to start. So where do we? So New Relic. Let's talk about New Relic. I love New Relic. I don't work for them. However, if I talk about them nicely enough, maybe they'll give us smaller license fees next time. So New Relic I've been using for about 7 or 8 years. Probably from one of their earliest betas, in fact. And New Relic's amazing because it allows you to do something that is very hard to do. You can only really do this on the web. If you build a piece of desktop software and ship it, it's very rare for you to get an accurate application trace of how long every single thing took inside the application on that user's hardware, sent back to you every time they use it. And you could do that, but they'd probably complain. With web applications, because it's running on our stack, you can do that. You can actually look inside it, and New Relic makes that particularly easy. And so I would say that in terms of being able to identify those critical parts, this is probably the first place to start. Or a tool like it. It doesn't have to necessarily be New Relic, but certainly something that gives you the ability to drill down into multiple levels. So here's a classic example. My employer, our employer, most of us, have this crazy idea that people would like to buy each other Christmas presents. Don't know why, it's some social convention. And so around about a month before Christmas, we have Black Friday, Cyber Monday. And about a month before that, or 2 months before that, we'll start marketing campaigns, etc. And so we'll see traffic behave in a way that we don't see it in the rest of the year. And I've kind of like skewed the axes on this because obviously some of this is commercially confidential and we don't want the whole web to see it. This is basically Google Analytics. This is New Relic. And we're going to be talking about this a bit more as to what those bumps mean and all those different things. But as you can see, as we progress, we suddenly get very different traffic profile towards the end going through that period than we do at the beginning. So every year I've worked here anyway, a couple of months beforehand, we go, are we going to be able to stay up during that period? Are we going to be able to survive Black Friday? And how do we identify the bits that are going to go slow? So the first thing we do is we go into New Relic and we say, well, how's the application currently performing? And as you can see here, we have this massive green block and we have a massive spike. This is response time, overall response time. And we go, cripes, that looks bad. And we think, we're probably not going to be able to survive this because we've made so many changes and we haven't really made performance benchmarking critical to part of our development flow. We're going to have to figure out how to start load testing those critical components and speed up that performance. So we start drilling down into this. So what we're actually looking at, and I'm going to flick back and forth on this, so it does get a bit annoying. So that request response cycle in a bit more detail. So if you imagine when someone types in URL, hit censor, or they type something into Google and they click on a link, the first thing the web browser is going to do is it's going to look up DNS records. It's going to say, right, well, I need to figure out where this server is. And then what then happens is it gets an IP address. The IP address points to a load balancer, which then goes to an internal gateway service, and that routes traffic to an application instance. That gets bundled up for most applications into this green bit. It's called request queuing. Basically, how long does it take to get a request to an actual application instance? So when we see these massive green spikes, we go request queuing. Well, what does that mean? Well, we'll go inside a bit more detail. Once it's done that, the application looks at the request and determines which bits of code need to be executed. So if you imagine traditional Ruby on Rails application, you'll have something like a routes file, and that will tell you which controller and which method. So there's a bit of Ruby code going on there. Now, quite a lot of software out there on the web will often try and do some kind of optimization around caching. So they'll then have a look at cacheable components, see if like the cache needs looking up and things like that. And if there isn't a cache hit, it'll go and talk to some data stores, run some business logic, do whatever it needs to do. So in here, this blue is application logic. That's Ruby code in the case of this particular service. This dark orange is external service. I think that is SQL. The light orange is cache lookups. And the green is rendering. The dark green on top is the render time. It's that bit where it's trying to turn it into HTML or JSON, or XML if you're being particularly sadistic. And then it optionally might populate caches. So there might be those bits where it looks at the cache and it writes to the cache. They're kind of jumbled together into this light yellow kind of layer. So we can look at New Relic and we go, right, I kind of know, I've got an idea. It's request queuing. But sometimes there's a hidden dependency there. So there's an external dependency, and this is a real-world example. That caching behavior that we talked about isn't necessarily the answer. So cache keys can be quite expensive to calculate. If I'm looking at a particular page and it's saying, well, I think I've got a pre-rendered version of the HTML for this page, so you don't need to do all that business logic. It's already in the cache. You can just serve it. We have to give it a unique ID, and we have to make sure that ID is unique enough that if a different user with different parameters asks the same thing, they don't get the wrong content. So we have these cache keys. Those can be quite expensive to calculate, and in fact, in some cases, that'll go into the blue. Right? This is Ruby code. So you can actually, in some cases, in some controllers, in some services, you go, well, I'm going to do caching, and look, caching is so lightweight. It's this tiny, tiny sliver of light yellow, without realizing about half of your light blue goes in cache keys. Yeah, well, okay, that's a problem. And your cache might not be as fast as you think. And I'm going to talk about that in a bit more detail in a minute when we go into a little bit more detail. So in fact, funny enough, next slide. I forgot it was the next slide. So this is an example of this particular service in production. This is network traffic going into Memcache. So this application was originally deployed some years ago on bare metal servers where the caching was done in memory. And when it was migrated to running in the cloud, the decision was made to put caching over the network into Memcache. So someone who actually did the work is now kind of rolling his eyes at me. It's like, no, that's not quite right, Paul. Basically, our cache is no longer, although it's got Memcache in it, this cache is not in memory. It's in memory somewhere, just not on the application instance. It's about 10 milliseconds away over a network, right? And what that meant, in this particular case, we found there were some very key components to our application, this particular service, where for every 100 megasecond going in of user traffic, there's about 500 megasecond chatter with the cache. So you go, oh, we'll speed things up and we'll use this. In actual fact, you're just generating huge amounts of network traffic in the background without realizing it because you're not really looking at it. So this is Datadog. This is another tool that is awesome. Love it. And this basically just monitors our Memcache instances. And you can see quite clearly, we looked at the production load and we went and did some load testing, which we are going to get to. We went and did some load testing and we identified, hang on a minute, this is a bit weird. And we did some changes, and you can see we fixed it. That's something we fixed the network contention. And as a result, the overall network application performance improves. There's another one which is kind of interesting for us. This is also Datadog. So this is around network contention on the front side. So that first step where we're taking requests and we're trying to find an application instance to deliver the request to. So we're trying to find an instance of the application which will go and do that response. If you don't have enough of them, it'll hold them. It'll just build them up. So if I can only handle 1,000 requests a second, for example, and the traffic is around 2,000 or 3,000 requests per second, then they just get queued up on that top layer. So you can see here, this is an application trace of when we had particular problems where we're seeing huge amounts of demand here, another spike here. These are probably TV adverts, general noise across a very busy period. And so you start thinking, well, okay, I clearly have a network contention issue on the other side. So not only have I got a very busy Memcache stack, I've got a very busy API gateway type stack. So you start thinking, well, okay, how am I going to figure out how to fix all of this? And that's where we get into load testing. So the first thing about load testing is load testing, you should be saying, right, I'm going to, you could load test production, and we have, sometimes by accident. So you could do that, but you probably want to do this in an isolated environment. You want to be able to do repeatable results. You want to be able to conduct experiments. You want to have the scientific method around you. So a lot of people say, well, what we want is a production-like environment, and it should be as close to production as possible. And then we're going to put production-like load through it, and then we're going to see what it does. Well, we already know what it does. It does that, right? So I don't actually need production. Let's suppose production is incredibly expensive. Let's suppose it's 1,000 servers, right? So to go and do my load test, I'm going to say, well, I'm going to need to double the technical budget because I want to do these load tests. I want to be scientifically accurate. I'd argue you don't, right? I can actually say that you could probably do a delta. So this is from a staging environment where we do some load testing. And you can kind of see here, we do an experiment where this request queuing problem is there in the green block. This is over quite a long timeline, so you can't actually see the individual experiments. But then we make some changes, and we suddenly see it halves. And we carry on messing around with settings. We keep on looking at different code paths and whatever. And eventually we hit it, and we get nothing. And then we try and break it again, and we break it again with some other kind of configuration. So that environment is actually relatively like production in this particular example, but much smaller. And that's because all I'm looking for is the delta. I'm just looking for a difference. So I can be driven by production metrics like these. I won't get back too far. I can look at production metrics, and then I can then say, well, I'm actually going to try and repeat that in a smaller environment, and I'm just looking for a difference. If I get twice the performance, does it mean that I'm going to get twice the performance in production? No. I can't have 100% confidence in saying that. But I can probably say I've got enough of a hunch to say, let's put that in production and see what happens to the production graphs. So I've isolated my problems in production. I've then been able to repeat something like it in a smaller environment elsewhere. I've then been able to modify my code, optimize it, run my experiment again and see the improvement. And now I can then ship that to production in the hope, with the hypothesis, that it will work. Does it always work like that? No, but it's a start. So one thing I would say is quite important is making sure that the load that you're using in these experiments, the traffic you're putting through, is representative of real-world traffic. So if you say, well, I don't know, suppose you're going to say, well, I'm just going to do 1 million requests a minute on the homepage. The likelihood is that you'll never actually do 1 million requests a minute on the homepage. You're likely to get some people looking at the homepage, some people looking at other parts of the website. And actually trying to understand that mix is quite important. And so what you actually want to do is what we call a blended test, where you take a sample of data of real-world traffic from a previous point in time, similar to the point in time you're testing for. You grab all that data down, and you do stuff with it, and then you use that as a kind of representative example. We use Google Analytics, so our load testing tool goes to GA via the API, and we say, I don't know, give us Black Friday of last year, 5 days worth of traffic, give us a representative sample, goes and grabs that, and then it turns it into magic stuff, which I'll talk about in a minute. You could do it with server logs. You could make it up and take a guess, but it's probably not going to be as effective. But it should be as representative as possible, because then you can be confident that your application is behaving, although it's in a smaller environment and it's not quite the same, you're relatively representative in terms of, well, I'm only going to hit this really expensive method over here 1 time in 1,000, and this really cheap one that gets hit 20,000 times a second, I'm going to be hitting just as much as it would be in the real world. And so it becomes a representative makeup. Actually running those load tests, JMeter is awesome. If you're not familiar with it, go find it, even though it is written in Java. So JMeter is awesome. The way we prefer to play around with it here is to use Flood.io, and that just basically means we can spin up a grid. It used to be that you could have a maximum grid of 20 servers, which are basically running your tests or actually hammering it. You can now get up to, I think, 99. They changed it a couple of months ago. And critically, is having these same metrics in your environment. So that is one thing that does need to be production-like. So you might not have the same number of servers, you might not have the same size of database, you might not have the same everything, but you should definitely have the same metrics. Try and get the same traffic, try and get the same metrics. So in the same way that we have New Relic and Datadog in production, in our environment, we also want to get that in staging. And the reason for that is that we can then basically kind of get a feel, is this experiment like what I'm seeing in production? Is it similar? If you're looking at completely different things, like we could just use like StatSD or whatever, or Splunk or whatever, but then we're not going to be comparing it in a way that feels intuitive. I don't know what that last sentence was about to say. It's critical to be able to... I missed the end of that sentence. I think it's critical to be able to replicate these results in staging and being able to analyze them and compare them side by side. Now, when we had this problem last Black Friday, we thought, I know, let's use a CDN. Let's just put a CDN in front of the website. And you go, that'd be awesome, right? Because then I don't care about my application performance because the CDN is going to fix everything. Well, no. Well, maybe, right? So the important thing to remember about CDNs is that if you build your application with a CDN in mind, it's super simple. If you build an application on the assumption that every response will be built by the application server, it's going to be a lot more complicated. So that can be extremely expensive to try and fix, something that many web development shops have found. And so that, if you can do it, absolutely, because it basically means that you can go, well, I can be a bit more forgiving. There's still a problem, though, that your CDN is still going to have to call your application at least once in a while. And it's still going to have to be able to get that, and basically all the CDN is caching it at the edge of the network. It's still going to have to be able to go and get reasonable performance. And some CDNs are quite aggressive with their timeout. So if you've got a request that suddenly you just don't care, and it's taking 10, 15, 20 seconds, well, your CDN is just going to start giving up on you, and deservedly so, right? Also, when you put a CDN in front of things, you think, well, I'm going to load test it. I have accidentally load tested Cloudflare, because I didn't realize the CDN was actually in place. So there are some complications if you actually want to understand real-world performance of your CDN besides that. First of all, let's suppose I go and build a grid in Flood.io, and it's in Ireland. When those servers say, I want to go and look at www.whatever, those DNS lookups, the CDN's DNS servers will give it IP addresses that are all very close to Ireland. Right? It won't give servers that are over in Japan, because that's very far away. That's silly. To get the IP addresses over in Japan, you need to run your tests somewhere close to Japan. So what you then have to start doing is start saying, well, it's no longer just enough to be able to say, I'm going to have 50 servers. I'm going to hammer it. You have to say, well, 70% of my traffic is from the UK, 30% is from the US, 10%, whatever. Start splitting it down, and then start building your grids up in those particular areas in order to get a representative sample of how your CDN's performing. Obviously, it just masks application performance, so you should still be load testing your actual application, because I suspect that CloudFront and Cloudflare engineers are probably quite good at making their code fast. So you're not really getting any information about how well it's performing. So you should really be testing Origin anyway. You can get strange results. I was going to put a slide in here showing our rather mad results, but they still don't make any sense to me. Basically, what can happen is JMeter can get very confused because of the way some of the CDN headers are passed, I think. So, in summary, performance optimization isn't evil. Even premature optimization is not evil. In fact, your job relies on it. If you don't do it well, then eventually the company that you work for will run out of money, or it'll be less able to hire new friendly colleagues for you to work with. Use New Relic and Datadog everywhere you can, or decent alternatives. Certainly something that is doing high-level application performance management and low-level kind of component tracers. I argue you don't need perfect production clones to get meaningful results, providing you understand how to compare a delta and you have reasonable expectations of what that involves. Getting real traffic profiles is pretty important. JMeter and Flood.io makes all of this a great deal simpler, and CDNs aren't magic. Thank you. Any questions? Yes.
Should we have a sort of a company-wide approach or a company-wide standard load testing, or should each team be allowed to go away and do their own thing?
So I've talked about, I didn't really mention it in this talk, but I've talked before about how you make a decision as to what's going on. I think, right, so intuitively, you've probably got a reasonable idea that this code is going to have a performance impact. And intuitively, as a developer, you should be able to say, well, I might want to load test it if I think it's making a lot of extra SQL calls or a lot of extra data store calls. And we should be able to trust developers to just be able to go in. I think company-wide policy, for me, I think, right, so not on the high street, we often really put this center of attention when we're going into very high trading periods. And when we're in lower trading periods, we're less inclined to worry about it because the traffic's so low in relation, it's still quite high, but in relation to those high traffic periods, that we think, well, actually, it's not quite so important because I could just scale a bit more, whatever. But I actually think we should be looking at trends almost weekly or monthly. It should be a constant thing where we're saying, well, actually, overall application performance has declined. These things are getting slower. Ideally, automate that. You know, this particular component is now taking 15% longer than it did a month ago.
Every day is Black Friday.
Yeah, every day is Black Friday is a good way to do it. I think, you know, basically what the traps you fall into if you say, well, I'm only going to do this in particular periods of the year, is that suddenly, let's suppose your marketing team have an amazing idea and it goes viral. And they just say, oh, well, actually, we're going to be on the 6 o'clock news tonight, and we're going to be on a chat show, and we've got like film stars are going to endorse us, and it's going to be amazing. And you're like, okay, well, actually, we're not prepared for the traffic. That's terrible. You're going to lose that opportunity. So being able to say, well, actually, at any point, we're good to go is really important. So it's like a hygiene factor. The problem is that because you can't say in advance, this bit of code is going to be slow, and nothing is right. You can't just say a priori, this bit needs to be optimized. But whenever you deploy something, you should go back and say, well, actually, how well is that doing? And is there anything I can do to make that faster? Is that actually a problem? And certainly if you're refactoring code, you should be saying, well, I've just refactored this code. I've added functionality. I've changed the database query. I've changed the way we use Elasticsearch or whatever. You should be going back a few days later and saying, well, what did it actually do to the application performance? Hopefully, it's dropped, right? You've improved it. But if you haven't, go back and improve it. Hello.
Is there a way you can get this into integration?
So you could do, one of the other talks, we were talking about the pyramid of tests, right? So you could argue smoke testing for key critical paths. So you could say, well, okay, I'm going to do like you might do with code coverage or something like where you're saying, well, I kind of want to know that my code coverage is up there, or very high level kind of integration tests. You could do something where you say, I'm going to have a separate job, which is just going to go and do that. For that, it's harder to use tools like Flood.io, but you could use other tools. You could use JMeter to do that. You could test a QA environment. Different languages and different frameworks have got different approaches. These services specifically, we're talking about high level Ruby on Rails, web application integration. Performance benchmarking, Rails isn't great, so you kind of have to go from the outside in. You could do it. Would you mark a build as failed if it gets slower? It's pretty aggressive. Well, I think that's quite aggressive. But what you might do is you might alert the team and say, look, your last commit just slowed down this critical path, like, you know, from say homepage to checkout. You've slowed it down by 15%. Every single page is now slower. You should go and have a look at that. You could, if you found that you really want to make it central, say, no, you have to be faster or at least as good. But then, there's always margins of error on this. So if it's like 5% slower, it could just be a testing error. Hello?
How do you make it so that everyone understands what the results saying? But like you get over the first hurdle of doing the next. The next thing is understanding those results, making sure that you take them action.
So I think that's quite tricky, right? So if you go back to graphs like this, right? So I know what each of those components means because I suppose it's my job to, right? So I know what each of these bits mean, and I know which bit of the stack is responsible for each bit of the color. And in New Relic, you can actually drill down if you wanted to. So you can say, actually, I want to have a look at this particular controller in a Rails application, or I want to look at this particular code execution path, and it'll say, right, I'm spending 80% of my time here and 15% of my time here. And so you say, well, okay, that 80% of your time, and you're being called 1,000 times a minute or whatever. You say, well, okay, if I can get a 10% gain in that, then that's awesome, right? So you can start to zero in, like, these are very high-level graphs. New Relic has huge amounts of depth to it, especially with the production load. And once you start getting into it, it can be quite descriptive to a level where a developer goes, oh, okay, like literally line numbers, source code file numbers in Rails. It'll actually say, this particular file, this line number to this line number, I'm spending 75% of my time here. Fix that. It won't tell you to fix it. It'll just tell you that this is how long it's taking. So there is an argument that more developers need to be more familiar with these tools. So do more training, things like that. Get more developers to watch this talk. That'll be a start. But yeah, I think it can be quite complicated, particularly if you're not used to looking at this on a regular basis to parse it and understand it. Yes.
We're running in AWS.
Yes.
AWS resources are, my knowledge, why can't they just throw money at the problem when the problem occurs rather than sort of like spending a lot of time and quite a lot of complicated and difficult engineering?
AWS may be infinite, and to be infinite, their budget might be infinite, but is yours? Probably not, right? So first of all, you have to go back to this thing I was saying before. Slow applications, very poor for an e-commerce company, right? Very poor, right? You go back to these, the value that, okay, right back here. If you go back to the reason why performance is important. So from the customer's point of view, it's higher. If you have fast applications, you'll have higher conversion, you'll have higher return rates, and you'll be more valued, and therefore your business is more valuable. It doesn't matter that you're saying, well, I'm going to just shove a load more instances up and like, oh, that'll look after it, because you're still not going to have the conversion rates you would have had if you just fixed it. And secondly, all of this is running on the hardware you pay for, so therefore you're going to have less money at the end of the month, because you've gone, well, okay, application's a bit slow, I'm just going to have like twice the number of servers. Well, now you've got twice the number of operational expenditure. You've just doubled your budget. So that means you no longer have as much profit. You no longer have the ability to hire as many lovely people or spend on marketing or whatever. So you can, the cloud's not magic, right? It costs money. It might be infinite, but only if you've got infinite money. So you kind of have at some point to say, I have to get a return on investment. And therefore you're probably going to fix your budget, which means you have fixed capacity. Or you're going to say, well, I'm going to be quite free and easy with my budget. In which case, okay, you're going to be less profitable and your customers are going to be more fed up. Does that answer your? Mm-hmm.
I don't know.
It's always the way, Tony, always the way.
It is. When Peter was writing, optimization was mostly a case of it was optimizing the process about it. So you would look at a problem and you would go, oh, it's taking a long time. I need to unroll this loop. I need to anchor this bit in assembly. For that reason, writing optimized code was hard and difficult, and it added depth to the project to make things more difficult. Whereas what we're talking about when we're talking about optimizing, most of the time, what we're talking about good architecture.
Yeah.
We're saying, I want less fetches from that cache. I want less network traffic generated by this process. And those things are about good code because they're about getting architecture right.
You're right. So quite often, right? So often when you start looking at like performance enhancements to websites, right? I remember years ago, people go, oh, I can make my website really fast. you're serving static content, right? So there's these stupid challenges like trying to get 10,000 concurrent users on a single VPS or something, and by tuning Nginx. Static content's a relatively simple thing. And that basically is, how do I handle TCP connections adequately? And then with web applications, it becomes more complicated because you might have some network bound stuff. And it's a bit weird to think of a SQL query that takes a long time as being network bound, but ultimately it is from the point of view of, it's just like the same as slow disk, almost, right, from the application's point of view. So there's that, but then there is actually business logic, right? So building those HTML templates or doing some logic, and if you have something that's incredibly slow and is very CPU intensive, then you're back in the same problem, right? I think trying to bring the NUF kind of analogy up to date is a lot of the things that they were concerned about, we don't care about, right? We don't care about trying to find the index of a value in an array. We care about, hopefully, less trivial things that are a bit more complicated. But what he's basically saying is, if you go and identify, so go and measure things constantly, and then you go, oh, that looks a bit slow, go and try and understand why it's slow, then go and optimize it. And sometimes you might just go, well, it's the network. Well, try and avoid the network. But you're right, it's a very different thing. I think if Dijkstra was alive today, he would be quite confused. Well, he wouldn't be confused. He's a very, very smart man. But I think he'd find it very difficult to rationalize some of the statements he made in the context of cloud applications, because even now we're only just starting to learn how to build distributed applications in a coherent, logical way. And this even gets even weirder when you start talking about functions as a service, AWS Lambda and things like that. So in fact, actually that's a good point. With Lambda, you pay per 100 milliseconds per 128 megs. So if you use slightly more memory, because you go, oh, well, I don't care, I'm just going to use a bit more memory, then you pay double the price. Right? If you go over 128 meg, you go up to like 190, up to 256, you pay double the price. If you're using Java, JVM, you have to use 512 meg, so you've got quadruple the price. So you go, oh, maybe I shouldn't use Java. I know I'm trolling. But then if you say, well, this is relatively slow, and AWS say, well, you can have like 5-minute timeout. Well, how many 100 millisecond blocks are there in a 5-minute timeout? Don't go there. Get it under 100 milliseconds. In fact, get it under 50. And it's I think it's a challenge trying to figure out some of this stuff, which is kind of deeply ingrained into computer science brains, is having to be updated in this new world and this new architecture. But there are lessons still there. I don't think we've extracted them all yet. Right, thank you then.